the rest of the talks. So it's definitely not related to birational geometry. It's related to moduli somehow. And it's more close to differential geometry in a sense than algebraic geometry. But at least the kind of differential geometry we discussed is contained in the Lazarsfeld's book. So anyone who studied it carefully should be able to follow. So let me recall the basic definitions. So we are looking at, let's start with the algebraic geometric side. So X is algebraic curve. Over C of G, and let Gx be the genus. And we assume that it's at least 2. And then there's this notion of gonality. And this means that it's the minimum degree of surjective morphism to P1. And of course, when the gonality is 2, this means that the equivalent saying that X is hyperelliptic. And then it is well known that the gonality takes the following values, that is at least 2 and most is about half of the genus. And there are algebraic curves taking arbitrary values of gonality between these two values. So in other words, when you look at the moduli of curves, there's a stratification of this moduli space by gonality, where the deepest strata is when delta x is 2, and then there's some other variety containing this with a larger value of gonality and so on. So this defines the stratification. Okay. Now let's go to the more differential geometric side. So here X is now equivalent to a compact Riemann surface. And since it's genus LS2, this is hyperbolic type. So which means that you can write X as a quotient of the disk by some subgroups, where B is the disk, the unit disk, and gamma is inside the biholomorphic automorphism group of B, and this is co-compact and discrete. So that's the Riemann surface. Now let's denote by dB the distance function with respect to, there's a natural metric on B with respect to the hyperbolic Taylor form omega, which is omega B. I forgot 2. No. This constant I never get correct. This is minus 2 d. Okay. So there's a natural Poincare metric. So we denote by d lower b the distance function with respect to this Poincare metric. And then we define the following. The injectivity radius of x. This is denoted by rho x, and this is 1/2 of minimum and G is in B. That's the definition of injectivity radius. And if it's not easy to visualize, you can also define it as the twice of injectivity radius is what's called systole of x. And this means it's the length of shortest closed geodesic. So when you have your Riemann surface, so systole means it's the shortest geodesic. It's here, for example, here you can put it here. Closed geodesic, the shortest closed geodesic, and the length of this is what's called the systole. And the injectivity radius is exactly half of this. And this means that for any point, and if r is smaller than injectivity radius, then there exists a geodesic ball P x r centered at x with the radius r contained in x in an injective way, injective geodesic ball. Well, in this case, it's disk, of course. So namely, this disk do not intersect itself. So you can, at any given point x, you can find such a large disk with the radius less than the injectivity radius. But if the radius is bigger than the injectivity radius, then there are some points where the ball intersects itself. So this is called the injectivity radius. And this name is a very funny name, this systole. Gromov gave this name. It has to do with the state of your heart when it contracts most. So that's the geometry.
You have two different blood pressures.
Okay.
And then you do 120, 180 or something.
Okay. So this is a very natural notion in differential geometry. And one interesting thing is this rho. So at each point of Riemann surface, you have this function, this constant, which is positive constant. And in other words, you have this function from moduli of curves to positive real number, the injectivity radius function. And this function is actually continuous. And it's a kind of Morse function. So it catches some part of topology of this. But it's not very well understood. So now you have two geometric objects here. One is this algebraic stratification given by the gonality. And then you have this function given by injectivity radius. And so the main question I was interested in is the relation between this function rho x and the stratification. So what's the relation? That's the question.
Is there any relation to the periods?
That we'll discuss slightly, but not much relation. Okay, so that's the question. And of course, what kind of relation do you look for? That's another question. So you don't just start with the aim of finding some relation between these two. Is quite arbitrary. And there was a more specific motivation I had. So let me tell you this motivation. By the way, this was all joint work with Lincoln Toll in Singapore. Okay.
But in the first definition you gave, it seems that this invariant is some kind of holomorphic invariant, but in the second definition it's kind of Riemannian invariant.
You mean this first one?
The first one, it depends on the hyperbolic the Keller method.
Yes,
it's
yes.
kind of holomorphic
Yes.
invariant. But in the second definition, just the closed geodesic.
It's geodesic with respect to the hyperbolic metric.
With respect
Yeah,
to
yeah,
with the Riemannian
yeah.
method.
That's one point you have to. Yeah, I have to mention. This is with respect hyperbolic metric. There's a more general notion with respect to arbitrary metric. We don't. We are only looking at hyperbolic systoles. Okay. Now, the motivation we had was the following. So this is a more specific question than this arbitrary question. And for that, I define another notion. So we define the notion of a tower of Riemann surfaces, compact Riemann surfaces. This is a sequence of compact Riemann surfaces of atal coverings. Okay, so you have a sequence of atal coverings of a given compact Riemann surface, and this means that you are given the fundamental groups, gamma 1, inside the automorphism of the universal, the disk. So such a sequence corresponds to sequence of subgroups. Now we assume that we say that this sequence is a tower of a compact Riemann surface if such that atal coverings given by such a sequence of groups such that the intersection of gamma I is identity. So this is modeled on this congruent, taking the congruent subgroups. So you take, they converge it to the universal cover. So not all sequences are of this type, but this sequence is more natural in a sense. But now this condition is exactly equivalent to saying that the injectivity radius goes to infinity. So that's equivalent. That's the notion of a tower. Now there was this somewhat curious result of Psyche Young in 2000. He says that given any tower, there is some I such that Kxi is very ample. So actually he proved it for a more general situation, for arbitrary locally symmetric space, tower of locally symmetric space in higher dimension too. But in particular it implies this, that when you are given a tower, if you go higher enough, then the canonical boundary becomes very ample. Now of course this means that delta xi is bigger than 3. So it's not hyperelliptic. So that's the implication. So what he showed is that for arbitrary tower, if you go higher enough, the gonality is at least 3. That's what he proved. So it naturally so this suggests the following question. That given a sequence of Riemann surface, if the injectivity radius goes to infinity, then Does the gonality goes to infinity? That's the natural question. So here it proves that it's at least 3, but does it really go to, is it really unbounded? That was the question. And then the main result, our main result is actually an answer to this question. So this is with Rincon, and this here. And we gave the following inequality. So the injectivity radius, cosine hyperbolic of half of the injective radius is bounded by the gonality. So the interesting thing is it's independent of genus. So the Riemann surfaces of a fixed gonality, all genus, have a bounded injectivity radius. That's what it says. Okay. So this answer, so this is the main result that I like discuss today. Now, so we started working on this right after this in 2000. So it took quite long for us. And there are some reasons behind this. But let me first mention this result. There's one special case of this inequality which was known before. And this is when delta x is 2. So for hyperelliptic Riemann surfaces, this inequality, namely cosine, is proved by these guys. I never met them or never seen them. So it's complete strangers to me. Katz and Sa. These seems to be differential geometers or topologists or hyperbolic geometry. And they used using hyperelliptic involution. So they use the structure of hyperelliptic property very much. So as far as I see, you cannot generalize this to arbitrary Riemann surface. And then Jun-Muk 2. Now, one interesting thing about results like this is certainly it relates the different hyperbolic geometry to algebraic geometry. But there was results of this type before. And this was proved by Peter Lee and Yao in 82. What they proved was lambda 1x times genus minus 1 bounded by gonality. So here lambda 1x is the smallest first eigenvalue. So smallest positive eigenvalue. Of the hyperbolic metric, of the Laplacian. So this is another result which relates hyperbolic geometry to gonality. And it was funny, but initially we thought that we can use it somehow prove this kind of result by relating this part to injectivity radius, and we spent about 2 years on doing this but without success. And then what helped us was my another collaborator, Jun-Muk. We eventually told him that we are trying this but getting nowhere. And then he suggested do not try this problem because so his suggestion is this object lambda 1 has been studied in 70s and 80s by almost every geometers. So they knew a lot about them, and if they do not know it already, then there's no way that we can get a new result out of this. So I gave up, basically, around 2 or 3 gave up. Okay.
Can you say how this result there? How was the first theorem proved?
This one?
Yeah.
This one is, you look at the Bergman kernel. It's property of Bergman kernel. The canonical system is embedded in the Bergman kernel of the, so by looking at it. It's not very, how do I say, according to him, it's not very deep theorem. Okay.
And the formula was in the second paper or?
This formula?
Yeah, so I mean,
A second paper, what do you mean?
no, in that paper, the formula was written in that.
This one?
Yes.
Yes, it is written there.
I see.
Yeah.
You're proving that if there's a covering of small degree, then there's a very short geodesic.
Yes. Yeah.
Just reading this text.
You say that if you have a covering of small degree, the geodesic is bigger than this cover, but why more? Cos
No.
rho x lesser than the length of the geodesic.
Rho x
No, this is gonality.
twice rho
This is gonality. This is.
I inverted that.
My sister.
I inverted.
Okay, so we basically stopped in the middle around 2 or 3. We basically gave up. And after that, we don't see how to proceed any further. And then, luckily, there was another inspiration. And this was, so our proof is essentially inspired by the following work of Lazarsfeld. So let's look at, so there's a work of, so this has to do with the period. So the Jacobian of X is a torus, of course, and with a polarization, theta divisor. And then there's a notion of what nowadays called Boozer-Sarnak invariant. And this is denoted by M X. And the definition is very similar to injectivity radius. So you look at the length of the lattice vectors and the minimum of the length of lattice vectors, where this length is with respect to the Euclid metric determined by the second value. So in a sense, this is square of systole, the systole of Jacobian. So it's roughly injectivity radius of Jacobian. Well, it's square or twice square with respect to Euclidean metric. Now, there was a rather small theorem of Lazarsfeld that which appeared in his book, and which says that 5 or 4 this Boozer-Sarnak invariant is bounded by the gonality. That's his result. It's essentially, well, I'll explain how he proved this. And so what happened was after we gave this up, I was browsing his book and discovered this inequality. And it looks like something very similar to what we've been looking for, that on the left-hand side, there's this injectivity radius or systole. Right-hand side is the gonality. It looks very similar. So it's, then we try to as Radu suggested, we try to look for the relation between this, the period and injectivity radius. So if you can relate the period to injectivity radius, then you can use it to prove a result like this. So this we tried another few years without much success. And I think it's very subtle, the relation between although they are essentially the same kind of object. This is with respect to Euclidean metric of Jacobian, and this is with respect to the Poincare metric of the curve itself. Very similar concepts, but the relation is very subtle. And there's, as far as I see, there's no direct relation. You cannot deduce that from here. So naturally, the next step is to look at the proof, how he proved this. Then maybe try to modify the proof at least in our situation. Okay, so let me tell you how he proved this. The key point of this proof is the following. So maybe I go over there. Let's see. So the key point of Lazarsfeld theorem is the following. It's called Federer's inequality. And it's in the following setting, you look at the ball of n-dimensional ball of radius r in Cn. This is a Euclidean ball, and then now Vk. This is a closed k-dimensional analytic subvariety. Contained in the ball. And then you can ask how big is the volume of this analytic subvariety with respect to the Euclidean metric. And Federer's inequality says that this volume is at least the multiplicity of this variety times the volume of k-dimensional linear ball. This is linear ball. Linear sub-ball. You know what I mean?
You mean that Vk is the intersection of the ball with a closed k-dimensional?
You can say it that way. Or Vk is a closed variety inside the ball.
What's its multiplicity?
Multiplicity, this is analytic variety, so multiplicity at the origin.
Oh, I see.
So there's the origin. Yeah. So let me draw the picture. So you have this big ball. And the center here, and then now we have our analytic variety. I don't know how with some singularity there. And then what he says is that the volume of this guy is exactly equal to something like this. So this is Vk. But you have to count as many as the number of multiplicity. So if the multiplicity is 3, then you have to get 3 of them. So the volume is at least as big as this. That's what it says. So this so that's the inequality. So So it's a lower bound for volume in terms of the multiplicity and the radius. That's Federer's theorem. Now, using this, it's very easy to prove Lazarsfeld theorem. So the idea of, let me just give you idea of proof. So suppose you are given this finite cover to P1. And then of degree delta x. Then out of this, you can cook up a curve. So from this, you get a curve C inside x cross x. And this curve corresponds to the graph of f. So this is correspondence graph. Namely, 2 points which are sent to the same point. So this way you can cook up some curve here. And the cohomology class of this curve is, you can calculate it easily, where D is the diagonal. So this is what you use out of Gonality to deduce the existence of such curve with such property. And then the rest is easy now. And then this C gives rise to a curve. I mean, this part is a little bit not precise, but just to admit this. Okay. So using this, you can produce some curve in Jacobian, basically by the difference map, such that the volume of V over multiplicity of V is roughly the Gonality. And this comes from these numbers, basically. So let's admit this, okay? So using the Gonality, you can produce a very special curve in the Jacobian, where the volume over multiplicity is roughly like Gonality, modulo some constant. Now, by Federer's theorem, Federer's inequality, this one, volume over multiplicity is at least volume of V1 of R. Right. R is now this User-Sarnak invariant, roughly. So maybe I'll just write R here. And this is roughly the User-Sarnak invariant of the Jacobian modulo some constant. So this way you can see that delta x is bounded below by the User-Sarnak invariant of Jacobian with modulo some constant. And that's how we prove this. Okay, so, and then we try to modify this to our proof. How to use this? I mean, initially we thought that, well, you have to use this. And actually, as I mentioned later, we have generalization of this theorem. Earlier, we have generalization of Federer's inequality in arbitrary Hermitian symmetric space, in particular, like product of two Riemann surfaces and so on. So we had a very general form of this inequality. So we tried to use it to deduce something like this, but it also doesn't work. So for a while, we were very puzzled. And then, luckily, about 2 years ago, we realized what we have to do. So, so it turns out that our main theorem can be proved by a similar argument. If we replace Federer's inequality by another one. So what we really need is to replace that guy. This part is okay, but you need a new inequality. So that was the difficulty. So let me state what's the new inequality. So to state the new inequality, I need to define something. So let's define. So let's denote by dx the distance function on x, and then for each r less than the injectivity radius, define the geodesic tubular neighborhood of the diagonal so I denote it by WR, and this is so the picture is following. You look at the product of x and x, and here's the diagonal. Maybe I'll write it. This is diagonal. And this WR is a kind of tubular neighborhood of this diagonal. And this looks like this. So this is the WR. Where from here to here, this is R now. So this is WR. So you look at this tubular neighborhood. And because it's smaller than injectivity radius, this is a kind of very nice neighborhood of the diagonal. There's no intersection, self-intersection. And then now this part, for each x, there exists anti-diagonal inside WR. And this roughly looks like, for each point x here, there's something which is kind of orthogonal to this guy. And this is called the anti-diagonal over here.
Are you using the GRD? You using
GRD?
understand what's happening?
No, I'm not using anything so far. I'm just using a Riemann surface.
What does anti-diagonal means perpendicular?
Yes. So this means not. I'll explain. Okay. This exists for any Riemann surface. So there exists some curve, which is kind of orthogonal to this, which is nothing but this. So corresponding to so in the universal cover, there's something which is perpendicular to the diagonal, G and negative G. And at each point, because it's inside the injectivity radius, they go down to define a curve here. So this exists at every point. And conceptually, this comes from the fact that this is a symmetric space. There's involution of a matrix. It's a locally symmetric space. So locally there exists involution, but it's inside the injectivity radius. But what's true is that this statement is true. There is curve inside this tubular neighborhood, perpendicular to each diagonal at each point. And they are kind of all isometric. So such a curve exists. Okay, and then we are ready for the new volume inequality. So the result we really need is the following. So here's our new volume inequality. And it kind of looks very natural that why people, it's kind of surprising why people haven't discovered this before. So for any closed one-dimensional analytic variety, V inside WR, and R is less than our injectivity radius, the volume of V. So now V is something in a curve here, inside here, like this. Okay. So this is our V now. So we are trying to measure the volume of this guy. And the volume is measured with respect to the Poincare metric. The Poincare metric on the x cross x. So that's the volume. And this volume is at least, it's similar to Federer's inequality in concept. So here, one point corresponds to the diagonal. So the multiplicity should be replaced by the intersection number, V and D. And then what's the minimum volume? The minimum volume is exactly volume of the anti-diagonal. Okay. So that's the statement. So in other words, this guy, this blue guy, to the volume of this blue guy, you count the 4 intersection number, is at least as big as 4 of this. That's what it says. And yeah, and this was the key. So if you replace, in Lazarsfeld's argument, if you replace the Federer's inequality by this volume inequality, then you get our bound between injectivity radius and gonality. So now the main problem is how to prove this. So up to here, it was done something like early last year. We realized that this is something we have to prove. Okay. So
does the original volume inequality follow from the
it's hard to say. It's not. You can probably use it, but the original volume inequality is nowadays 2 standards. So, I mean, it's very strange to say it that way. Because it's the Federer inequality is now embedded in all kinds of theory. So the kind of theory we use must have that inequality somewhere inside.
But is the original inequality a hard result or?
It's not hard. I'll explain the proof now. Of course, it's not easy to algebraic geometers maybe. But to differential geometers, they regard it as something elementary. I think in undergraduate, some undergraduate books already. So we realize that this is the inequality we have to prove. So we try to prove it using following Federer's, by generalizing the proof of Federer's. So let's look at the proof of Federer's inequality.
Before you do that, where does the hyperbolic cosine come from?
Do not. It has to do with. Okay. That's a good question. It's this guy. It has to do with the volume of the diagonal, anti-diagonal. Let me see whether I wrote it down. Here. Okay. This is easy to compute, and this is 8 pi. Okay. Maybe R here. R. Okay. Now let's look at the proof of Federer's inequality. Because that's what we need to modify this somehow to get this. Now I'm not going to give you details, but let me explain the ideas. There are many proofs, but the first proof by Federer is in the 60s. And this use, you may say that this is a degenerating V. The variety, he degenerates the variety somehow by radially. So that was his original proof. And then Lazarsfeld, I think it's in 90. I mean, his greatest contribution here is he proved his original theorem, actually, or something simpler than that. His theorem on 96 without knowing Federer's inequality. That's his great contribution. Because that way he proved Federer's inequality by a different method. So, in a sense, dual to this. So this is degenerating metric. The Euclidean metric. And so kind of dual argument. And this, more precisely, this is what he quoted, the idea of symplectic blow-up. Now, these two arguments are rather difficult to generalize to other metrics because they really use some radial degeneration. So you really need the radial symmetry. So actually, Winkeng and I had used this to prove a version of this for hyperbolic spaces. So rank 1. When the metric has radial symmetry, you can generalize it easily. But when there's no radial symmetry, it's very difficult to generalize this. And then later, with Winkeng, we kind of modified Lazarsfeld's argument. And the idea here is degenerating the Kähler potential. So instead of metric itself, we degenerate the potential of the metric. And potential is some kind of function. So it's much more flexible. So this proof is very flexible and works for arbitrary Hermitian symmetric space. So this is the kind of proof which is most easiest to generalize. And so here the main idea is uses Demais Stokes theorem, version of Stokes theorem. Okay, so I'm not going into details because certainly we don't have time. So maybe I'll just mention to you what is Kähler potential. So Kähler potential means when omega is Kähler form, you can locally always write it as dd bar or some function. So this function is Kähler potential. So this kind of function is what's called Polari subharmonic function. So if you write a metric as dd bar of something, then you can just use this function to degenerate the metric. And on a ball, in the case of Federer's inequality, on the ball you can always find such a potential function to degenerate the potential. Okay. Then what is the difficulty in our theorem? So the difficulty proof of this new Poisson inequality. Why did it take around 2 years to finish the proof? The reason is that this degeneration argument at the very first step fails. The fact is that there's no potential for our omega x cross x on WR. On this tubular neighborhood, you cannot find the potential function. And this is a general fact. When there's a positive dimensional subvariety, there does not exist potential function in that open set. But it's by maximum principle. So there's no potential function. You cannot.
So the D there has positive self-intersection. So you can't contract it to a point. You can't.
This can be contracted, but there's singularity.
It can't be contracted by an analytic map because D squared is positive.
No, D squared is negative. Yeah.
D squared is, I'm sorry, 2 minus 2.
Yeah. D squared. So when you contract it, the singularity, you cannot, yeah, that's one thing we tried before. By contract it and put it inside a ball and use Federer's inequality, but it doesn't, there's difficulty with the singularity.
Yes, yes.
So you don't have a potential function. So at the very first step, we try to degenerate the potential function, but there's no potential function. So what to do? So that was the problem. And then very naively, so we define a new notion. It's a very naive approach. So define a plurisubharmonic function f is a subpotential. I mean, this is very really easy thing. Subpotential for scalar from omega if this guy is less than this, it's not really inequality, but it's inequality. There is subpotential. And the thing is that to prove volume, to get volume lower bound, say, it's like you're calculating, say, k-dimensional variety. You calculate this current and integrate it over the variety, open set, say, and that's how you get the volume. But because of this, you can actually, instead of, I'm sorry, this must be wrong. Maybe square root 1, I somewhere, never mind. Okay, so if you replace this by the subpotential, the above subpotential, as long as you want lower bound for volume, it doesn't matter. If you get lower bound for this guy, then you still get lower bound for that guy. So to get volume lower bound, we can just use, we may use subpotential instead of potential. That's a very naive idea, and it's good. But the problem is then how to choose the subpotential. Because one obvious subpotential is 0, which will give nothing. So to get good inequality, you have to choose good subpotential. Here you don't have a potential, but you do have subpotentials, including 0. The problem is how to find a good one. And from here it was completely guesswork. And so what we did is we initially tried the obvious subpotential. There was an obvious subpotential starting with this guy. Now this guy is the distance from the diagonal, in a sense. This object is the distance from the diagonal. So we guess that the subpotential must be some kind of function of this distance from the diagonal. And then from the form of the metric omega, we guess this must be a good subpotential. It turns out that this is a subpotential. But it's not good enough. It does not give our inequality. So it's not good enough. This is a subpotential. but not good enough. And then what we did is we tried to modify this now. And then eventually write down some differential equation, inequality, in terms of this. So to find the optimal, so try to find optimal modification of this. And finally, so I will just write down the answer. The optimal subpotential turns out to be the following. So this part is quite same, maybe it was 1, but doesn't matter. And there's some other terms. So this is the function we want. So this turns out to be a subpotential, and if you plug it in, you get the inequality we want, this sharp inequality. And the most surprising thing for us was that it really worked. It gave optimal inequality there. Although this is completely obtained by guesswork. There's no reason why this would give the optimal subpotential. I mean, you would say you cannot prove that this is the best subpotential. So, but still, it is enough to give the inequality. Thank you.
What is the last term?
The last term is some kind of continuity. To get continuity along the diagonal, you have to plug. You need some constant term.
So it's still a function of the...
Yeah, it's a function on the tubular neighborhood. Okay, thank you.
So your result